Our final unit is on what's called multivariable calculus, and the good news is that there really isn't anything different about the topic of multivariable calculus, at least from the point of view of what we'll learn about in our class. We're going to talk about derivatives, and they really are the same thing that we did before. The reason that we include multivariable calculus is because it is an unfortunate fact that not every problem in the world involves just one variable. And in fact, as you go take other classes where calculus is applied, it's actually very unusual for a problem to only have one independent variable. So we want in our course to at least spend a couple of days talking about what should be different, what has to be done differently when we have more than one variable on a problem. And the good news is that we don't really need different rules. We just have to have a different mindset as we apply the rules that we already know. So one thing that you'll see that's different is when we have a multivariable formula, we'll still use our function notation, but you'll start to notice that there's more than one variable in the function. So we say f of xy, meaning that there are actually two numbers that you're going to be able to plug in to the formula, and we'll call the result from that z. It's possible to have any number of variables. This is an example of a function with a function notation using 3 variables, but there's no limit for 3 variables either. So the idea here is that you can have any number of independent variables going in, and then the result of your formula will be another variable coming back out. So here's an example of a cost function, and this is exactly what would happen if you had maybe a manufacturing facility where you have 2 pieces of independent information that determine your cost, and that happens normally when you would have maybe 2 different products that you build. So maybe $1,000 are your fixed costs; those are your, the rent you're paying on your building and the salaries you pay is $1,000, and then maybe you make one product that costs you $50 per product to make, and so your cost for making X of them is 50 times X, and maybe you make a second product that costs $100 each to make. So if you have $1,000 in fixed cost and it costs you $50 each for making item 1 and $100 each for making item 2, then this would be a realistic cost function for your business. The way we deal with function notation is exactly the same as we did before. When you see C of 5, 10, that means that the x is going to be 5 and the y is going to be 10, and you're just going to plug those numbers into the formula. So you see that taking our formula and plugging 5 for x and 10 for y would just give us a number here, and so that would be our cost associated with making 5 of object 1 and 10 of object 2. And then if the function has more variables in it, then you just extend the idea. So there's really nothing about this that's different than we do with functions with one variable. It just allows us to model more realistic things. So in my math lab, you'll see a few problems of that type, but it pretty quickly turns to problems like this, where not only are you asked to do something, but then you're asked an algebra problem to do with it, and that's just so that you get some more practice with algebra and start to think about what the limitations of this notation are. So, so we want to find all values of x such that f(x(x) equals 0. Well, what does f(x(x) mean? Well, that means in the formula for f, I should use x for x. That's simple enough. But I should also use the letter x instead of y. So in this formula, I'm going to use x like it's used, but I'm going to change the y's to be x's. So what you see here is exactly the same thing I started with, but the y that's there and the y that's there changed into an x there and an x there. So I've just used x in place of y. Now I want to figure out where that's equal to 0, and so that's just an algebra problem. And a lot of you are having a little bit of difficulty with some of the algebra problems, so I'm kind of going out of my way a little bit to give you some more practice with the algebra. So to solve this, I would first simplify the expression, and then if I have an expression equal to 0, I know that factoring the expression will allow me to solve that easily. So in this case, this factors into x minus 8 times x plus 1. It's easy to check that that has first times first equals x squared, and last times last equals negative 8. And the inner term is minus 8x, the outer term is 1x, so the sum of those two is negative 7x. So that works. So therefore, x minus 8 is 0, which happens when x equals 8, or x plus 1 is 0, which happens when x equals minus 1. So no matter how many factors you have here, you could have 5 or 6 factors. If you have a bunch of factors equal to 0, then you know that that means that one of the factors has to be 0. So regardless of how many there are, that you'll have that many expressions down here. So that would be our answer to that question. And again, the algebra there is not essential to anything that we'll be doing, but it just is a way of giving you a little more practice with the algebra. So here's an example of a problem in my math lab that that plays off of stuff that we've already done, but sort of tries to show the utility of having more than one variable available. So in this case, A and B are the prices of two different products that our store sells. So this is very much like what I was saying about our cost function. When we manufacture two objects, we want to assume we have a supermarket that sells two different vegetables, which of course is very realistic. In fact, it's not hard to imagine a supermarket wanting to have a function that used a variable for every single product in the store. So there could be hundreds and hundreds of variables in a problem. In this case, we're focusing just on asparagus and broccoli. So we have the price for asparagus per pound and the price for broccoli per pound. And we know that the amount we charge is going to affect the number of pounds we sell. That's just basic supply and demand. So we are assuming that these equations relate the price we charge and how much we can expect to sell. So X is how much asparagus we expect to sell, and Y is the number of pounds of broccoli we expect to sell if our prices are $A for asparagus and B for broccoli. So it makes sense that those things are all related to each other. Now we need the daily revenue function. Well, remember, revenue is a price times the number of items sold. And so we're used to seeing that process for revenue, but in this case we have two different prices and two different items. So our revenue is just going to be the sum of the two. We're going to have some revenue from selling asparagus. The amount of revenue for selling asparagus is the price of asparagus, which is A, times the number of pounds of asparagus I expect to sell, which is this value here, this 242 minus 3A plus 4B. That's how much asparagus we expect to sell at that price point. So that's my revenue from asparagus, and I want to add to that the revenue from selling broccoli. Well, the price of broccoli is B a pound, and the amount of broccoli I expect to be able to sell at this price point is 320 plus 5A minus 6B, which is described by the equation up here. So we can simplify that if we want to before we put it in the box. And I probably recommend simplifying it a little bit because it's just going to be easier to type in the box if you simplify it. And then we want to know R31. Well, R31 is just simply putting 3 in for A and 1 in for B. And that will represent the revenue that we can expect if we charge $3 a pound for asparagus and $1 a pound for broccoli. One thing that we'll see in this section is some pictures of graphs of functions, and we'll look at these pictures when we have, specifically when we have functions of two variables, because we can make an analogy that's pretty easy because we live in a three-dimensional world, so it's not too strange to specify things with three-dimensional coordinates. Now this particular picture again has drifted on me for some reason. These arrowheads are supposed to be at the ends of these sticks here, so let me just, this is a picture from the book, so you can find a better looking picture in the book. So, so the idea is that this is supposed to look three-dimensional. The X is supposed to look like it's coming out of the screen at you. And so we think of this area down here, the stuff on just this XY part, as being a regular graph. So if I wanted to come out 2 units along the x-axis and 3 units on the y-axis, I would sort of be walking out of the picture a little bit, and I would be right there. So that's the coordinates x equals 2, y equals 3. But we think of that as being like a point on the floor. Every point that we consider in our three-dimensional coordinate system also has a height. So you imagine when you see the x and the y value, imagine yourself walking out to a point on the floor. The z value is how high up you should be looking. or how low below the floor you should be looking. So the point that I drew right there was actually on the floor, and so we would say the coordinate of z there is 0. That point is 0 feet above the floor, but it's not hard to imagine that I might come up 5 feet high and draw a point up there, and if that was 5 feet high, then I would say that has coordinates 2, 3, 5. Because I walked out on the floor to the point where x is 2 and y is 3, and then I went up 5 feet in the air. So a three-dimensional coordinate system point is really just like a point in the room, not on a wall, not on the floor necessarily, just somewhere in the room. So wherever you are right now, your head is at a point in the room. Your head is a certain distance from the wall in front of you. It's a certain distance from the wall to your right, and it's a certain height above the ground. So your top of your head has an x, y, and a z coordinate using that idea. So for example, just to illustrate the problem that's in the book, and again the picture is drifting on me here, but 3, 1, negative 2 should mean coming 3 units in the x direction, and I have to picture that coming out of the page, right? This x-axis is supposed to be pointing right at you, out of your computer screen. Y value of negative 1 means going this way on the y-axis. Right? This is the positive y direction. So negative 1 would be there, and then a z value of 2 means that we would be going up 2. So you imagine yourself walking out to here, 3 units, then over 1 unit in the y direction, and then up 2 units in the z direction. Here's a better picture. And again, it's drifted on me a little bit, but this is supposed to be 3 units in the x, 1 unit to the left in the y, and then 2 units up in the z direction. You'll see my math lab problems of that type, and they try to draw a box here so you don't have to envision points drifting out into space. Coordinate of point E and F, well, E is right on the z-axis, so that one's kind of silly. There's no, if you're going to point E, you're going to start at A, and you're not going to go out on the floor at all. You're just going to go straight up the z-axis. So point E is at 0, 0, 1, 2, 3. So 3 feet above the origin. Coordinates of point F, well, for F, I would have to go 1 unit in the x direction, so here, so 1 unit in the x direction. I'm not going to leave that point. I'm not going to go in the y direction at all, and then I'm going to go straight up 1, 2, 3 units. So 1, 0, 3 would be the coordinates of point F. Finally, since we can plot points, that means we can draw graphs. And basically what we're going to do is consider a formula like x squared plus y squared. And we're going to imagine every single possible pair xy that exists on the floor. So you want to imagine walking out on the floor to the point x equals 1, y equals 2. Then walk out on the floor for the point x equals 2, y equals 5. So every possible place that you could possibly walk on the floor, you want to consider all of those possibilities. And then for each one, you're going to use the formula that's given to calculate how high up to draw a point. So for example, if I walked out to the point x equals 1, y equals 2, the equation tells me that I should draw the z value at 1 squared plus 2 squared. So that would be 5. So I can imagine this, then, is really just a collection of points, and it'll look like a surface. So by a surface, I mean it'll look like maybe like a parachute that's hanging over the room. And for any given point on the floor, every point on the floor is described with an x-coordinate and a y-coordinate. The formula is going to tell you how high up off the floor the parachute is directly above that point. So we have this idea of walking around and being able to look up and see a surface over us that's given by a point that comes from the formula. And of course that's a rough analogy because the z's could be negative. The surface could be below the floor, and we have to just sort of use our imagination for that. So some calculators will draw this. There's an applet that's linked in our custom contents folder that does a very good job of drawing this. Here's an example of a fairly complicated looking function. But you can see that if you think of this as sort of a billowing parachute shape, the floor, the xy axis is along the floor, and no matter where I'm standing, I can look up and see the surface directly above me. The height of that surface is going to come from the formula that gave me this graph. So it's going to be a z equals formula that I get from plugging the x and the y coordinates.